Hello, my darlings. Okay, so today we're going to talk about optimization. So first off, what is optimization? Optimization is the process of making something the best it can possibly be given certain constraints. It involves maximizing or minimizing a certain value or quantity. Sounds familiar, right? We've used the first derivative to find maxes and mins before. We've even used the second derivative with the first derivative to find maxes and mins. Okay? So, just like we've done before. Now, examples might be minimizing the amount of material needed to create a product, maximizing the profit of a company, minimizing the amount of time it takes to produce something. These are things, applications that are used in business, okay? Now, how do we go about solving an optimization problem? First and foremost, read the problem carefully, okay? Identify the information you have and the information you need to solve the problem. Draw a diagram if you can. Identify your known quantities. If you're minimizing cost or maximizing profit, write a cost equation or write a profit equation. Write an equation for the quantity you want to maximize or minimize. Use the constraints to find relationships between the variables. If necessary, rewrite the equation in terms of one variable. You only want one variable, okay? If it's possible, find the domain, because then you can use your first derivative test. If you don't know the domain, you cannot always use the first derivative test. Determine what values of the variable make sense. If you're talking about how much materials can be used, you should not have negative lengths of material. That doesn't make sense. Take the derivative. Find your critical points and your endpoints of your domain. Either use the candidates test with the first derivative, especially if you know the domain. If you're having trouble figuring out the domain, use your second derivative test to find any extrema, okay? Interpret the answer in the context of the problem. Remember, always check for reasonableness. If your answer doesn't make sense, go back. All right, let's try a problem. A manufacturing company has determined that the total cost of producing an item can be determined from the equation C, where X is the number of units that the company makes. How many units should the company manufacture? So they're asking us for how many units should they make in order to minimize the cost. So we're looking to minimize cost. Okay, so we need a cost function, which luckily they told us, and notice the variable is x. I'm going to call this C of x. 8x squared minus 176x plus 1,800. So our first step now is to take the derivative of the cost equation. So C prime of x, and sometimes you'll see them do dc dx, it's the same thing, equals 16x minus 176. Okay, not bad. We set it equal to 0. Now we need to solve that. If we solve that, that'll be 16x equals 176. And when we divide both sides by 16, 16 goes into 17 once with 1 left over, and 16 into 16 once. That means x is 11. Okay, so this tells us that 11 is a critical point of the equation. So step 2, we're going to use the second derivative test. So in order to determine if x equals 11 is a maximum or minimum, we're going to take the second derivative. So remember, our first derivative we just said was 16x minus 176. That means our second derivative, the derivative of 16x is 16, and the derivative of 176 is 0. Our second derivative is 16. That is always positive. Right? It's always positive. Since 16 is always positive, any critical value is going to be, now remember, if the second derivative is positive, that means the function is concave up. So sketch yourself a little picture. If it's concave up, that means you have a minimum, which is what we wanted, right? We wanted to minimize cost. Therefore, the company should manufacture 11 units in order to minimize cost. And that would be the answer to our question. Nice job. Now I know I walked us through that the way it was set up, so how can we recognize an optimization problem? First, it's going to be something like find the dimensions of the field with the largest area, find the ordered pair that is closest to a given curve, find the time when the particle is furthest from the origin, find the height of the box that will require the least amount of material. The words absolute extrema are rarely used in these problems, okay? Look for words like maximum, maximize, most, greatest, fastest, furthest. Or on the other side, minimum, minimize, least, smallest, cheapest, and closest. Those are keywords to look for, okay? Let's try another one. We're going to minimize the cost to build a box. Okay, so they even draw the picture for us. That's nice. We want to construct a box whose base is square that has a volume of 36 cubic feet. So I'm going to remember here, volume equals 36 cubic feet. Okay. And the material used to build the top and bottom, that's the blue sides, cost $8 per square foot. And the material used to buy the sides cost $6 per square foot. Determine the dimensions. So they want us to find the dimensions that will minimize the cost. So we are looking to minimize cost, which means we need a cost function. So how do we find the cost of this box? Well, the cost of this box is $8 per square foot for each of these sides. Now notice this is X and this is X. So this has an area, to get square feet, it's area of X squared. But you know what? This back side is the same one. So that's also X squared. We have two sides. So X squared times 2, right? So 2X squared, because X squared plus X squared is 2X squared. Then we need that the cost of the sides is $6 per square foot. Now let's look at the sides. So these sides that are not blue have a height of X, we have X, and then they labeled this side H. So that area is XH. But how many sides do we have? We have the left, the right, the top, and the bottom. So we have 4 of those, 4 sides of XH, okay? So that means our cost function right now is 16x squared plus 24xh. Now here's the problem. We have too many variables. We have an x and an h. Now I have more x's. I have an x and an x squared, and I only have an h. How can I figure out what that h is? Well, what I'm going to do, remember this volume. The volume of a box is length times width times height, right? The volume of the box was 36 cubic feet. And we have a length of x, a width of x, and a height of h. That means 36 is x squared h. So what is h? It's 36 divided by x squared. We're going to use this and substitute that into our cost function. So now our cost function, just in terms of x, is 16x squared plus 24x times, and we're going to put in that h, 36 over x squared. And if we simplify this, our cost function is 16x squared plus 24 times 36 is 864, and x times 1 over x squared is an x in the denominator. Okay, there we go. Now we're going to take the derivative. So c prime of x is going to be 32x minus 864 over x squared, right? Remember, this is 864 times x to the negative 1. So bring down the negative 1, keep the 864, x to the negative 2, which is why it's over x squared. So we want to know when the derivative is 0, and that would mean that 32x would equal 864 over x squared, or x cubed would equal 864 over 32. Now, 864 divided by 32, I'm typing that in my calculator, that's 27, which means x is 3. So now we have a possibility for where we're going to be minimizing our cost. We still need to do some more work though, so let's use that second derivative test again. Let's go back. Here's our derivative right here, right? We're going to take this derivative and we're going to find the second derivative. So the derivative of 32x is 32. And if I have negative 864 times a negative 2, that's a positive 1728. And now I'm going to have x to the negative 3, so it's over x cubed. Now we're going to take this second derivative and we're going to substitute in our critical value of 3. So we're going to have 32 plus 1728 over 3 cubed. Okay, so that's 32 plus 1728. 3 times 3 is 9, times 3 is 27. That's going to give us 32 plus 64. That is 96, which is greater than 0. And once you know it's greater than 0, you're good. If it's greater than 0, our cost function is concave up. And if we're concave up, we have a minimum at x equals 3. So we know the minimum is at x equals 3. But what did they ask us to find? They asked us to find the dimensions. So we know that x is 3 feet. But h is 36 over 3 squared. So that's 36 over 9, which is 4 feet. So the dimensions should be 3 feet by 3 feet by 4 feet. That is our answer. Fun, right? Yay! Okay, one more problem for today. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases. So we have this round volume, okay, but there's height to it. Okay, so it's more like a disc type thing. And you know I can draw, so please, bear with me here. You guys draw better than I do. Whose volume increases at a constant rate of 2,000 cubic centimeters per minute. A recovery device arrives on the scene and begins removing oil. The rate at which the oil is removed is R of T cubic centimeters per minute, where T is the time in minutes since the device began working. They want us to find the time T when the oil slick reaches its maximum volume. So we want to maximize volume. That's a bad thing, right? Maximizing the volume of an oil slick. They're trying to figure out when it's going to be at its peak, when it's going to be at its worst. Now, if you think about this, they already gave us a rate in and a rate out, okay? So they gave us the rate in, they gave us the rate out. That is the derivative function, okay? It's the rate in minus the rate out. So we already have the derivative, we just have to put it together. V prime of t is, our rate in is 2,000 minus our rate out is 400 times the square root of t. Now when is this derivative equal to 0? That's when 2,000 equals 400 square root of t. If we divide both sides by 400, the square root of t would be 5. And square it, t would have to be 25 minutes, okay, after the device showed up. So now, since we've done the other two with the second derivative test, let's go back to the first derivative test again, okay? So we're only going to start at time 0. That makes sense. So our critical value here was 25 minutes. Now, if you think about this, it makes sense that our domain is t greater than or equal to 0 because we're only working from when the device starts. We'll call that time 0, and this goes on forever and ever afterwards. We'll talk about our derivative on the top, and we'll talk about our volume function on the bottom. So if we pick a number between 0 and 25, like 1, and we plug it into this volume formula, 2,000 minus 400 times the square root of 1, that's a positive number. which means that the volume is increasing. If we pick a number bigger than 25, like 100, 2,000 minus 400 times the square root of 100, which is 10, times 400 is 4,000. So 2,000 minus 4,000 is a negative number, which means our volume is decreasing. So you can see our volume increases and decreases, and right here at 25, we have a maximum volume. So we're going to say, since v prime of 25 equals 0, and v prime of t changes from positive to negative at t equals 25, the volume v of t has a maximum at t equals 25 minutes after the device begins working. All right, and there we go. So, another way to think about that is the rate in was bigger than the rate out first, and then the rate out took over and became bigger than the rate in. Okay, so you can compare them that way if you want, but I think it's easier to do the number line or do your second derivative test if you have a critical value. All right, guys, so this is how we do optimization problems, and we'll definitely be doing more of these in class. Have a great day, and I'll see you soon. Bye.